Okay, and so today we're going to talk primarily about logistic regression, which is appropriate in instances where our dependent variable is binary or 0, 1 in nature, similar to the example we ran into on last week's midterm exam. And prior to getting into that, we'll provide a brief introduction to maximum likelihood estimation. Okay. And so, like I said, we'll do an overview of maximum likelihood with some simple examples, and then we'll talk specifically about the case of trying to estimate regression models where our dependent variable is binary, and some of the problems that we run into and that you all ran into during the midterm. And then we'll get into logistic regression, why we use this framework as opposed to linear regression, interpretation of the model results and parameter estimates coefficients, which is slightly different in nature from what we're used to with linear regression. And then we also have our, fortunately, last homework assignment of the semester has been posted. And so that'll be due a week from Sunday. And that actually is also related to stop-go decisions at signalized intersections using a slightly different data set. So you should be in really good shape to get started on that assignment immediately after today's lecture, basically. But that's where we're going in essence. And so before we get too far into things, like I said, wanted to introduce maximum likelihood estimation. I just want to get a show of hands and thumbs. How many of you are familiar with maximum likelihood or have at least seen that term used before in some form or fashion? And just to make sure everybody's with me, how many of you have not seen that term or not seen it used? Okay, so we got a fairly good mix here. And so basically, to this point, the method we've demonstrated for estimating regression models is ordinary least squares. We're trying to minimize the sum of the squared deviations of each individual observation from the best fit line. And so maximum likelihood is a different approach that we can use to estimate parameters in a model or in various other circumstances. Anytime we're trying to estimate parameters based upon some known or hypothesized distribution, we can often use maximum likelihood as a technique to estimate what we believe those parameters to be. Okay. And so as a simple example, if we think back to the binomial distribution, which we've used numerous times previously in this course, so we have some kind of process that we're observing that can be classified into a dichotomous outcome. So either yes, a condition is met, or no, it's not, or we see a pass versus fail, or a stop versus go decision, whatever the case may be. So those would all be characterized as a binomial distribution, where we might observe repeated scenarios of that same process of interest, and we would be interested in how frequently successes or failures occur, and then extending that further, understanding whether some factors increase or decrease the probability of success or failure. And so let's say, as an example, we've got n observations for our dependent variable of interest. And so we can consider the likelihood that we would observe any particular value of y based upon the parameters that describe that distribution. And so we'll use just the general term here, w, to describe any specific parameter that we're interested in. And so in that context, for a given sample size n and a given value of w, which in this case would basically be the average probability of success, or the probability of the outcome being yes, or y being equal to 1, essentially, we can determine how likely it is that we'd experience any number of successes, in this case, y within those n trials, essentially. Okay, so hopefully this looks familiar to everyone. And then by definition, that parameter w is going to range between 0 and 1. And so if we take a specific case of that binomial distribution, let's assume we're observing a process 10 times, and we're given that the mean rate of success or failure is 0.7 in this case. So W in the preceding example would be equal to 0.7. And so then just plugging in those respective values, we could use this probability density function to determine what the probability is that we would have 0, 1, 2, 3, all the way up to 10 different successes over that range of values. And if we plot what those probabilities look like, it's basically as you see right here. Okay, so the most likely number of successes, and this should hopefully be somewhat intuitive. If our baseline probability is 0.7, we'd expect 7 successes in those 10 trials. And then we would tend to taper off as we diverge from 7 or from that baseline probability of 0.7 in either respective direction. Okay. And so what we're trying to do in maximum likelihood is that instead of looking at the standardized distribution of y, so in the preceding example, we basically, we knew a value for a parameter w, and we could then calculate the probability of any value of y being observed among those 10 trials, okay, any number of successes. So in this case, we're going to basically work in the opposite direction. So given that we've observed this number of successes or failures, whatever the case may be, we're instead going to consider what the distribution of that parameter w is, okay? And so the way we do that is we establish what's referred to as a likelihood function. So instead of in the preceding case, our probability density function allowed us to determine how likely it is we would observe a specific value of y given w. In this case, we're concerned with how likely it is that we would see a specific parameter value w that would correspond to a sample data of y's, okay? So just basically flipping the context, but the same general approach is being applied here. And so if we think about that likelihood function, it's going to be very similar in nature to what we had seen previously, except as you'll notice here, instead of having our y's and n's here, we're those data are given by our sample, and so we're solving for the w, which was one of the given conditions previously. Okay, so we basically just reoriented this, and we're concerning ourselves with the distribution of w rather than the distribution of y based on w. Okay. And so from this, we can take this information and basically try to determine what parameter w would maximize this likelihood function for the specific sample that we've observed, okay? And so if we look at that function and we integrate that over various values of w, it should hopefully not be too surprising that at the end of this exercise, we come up with the same solution in essence. So just like we would see the highest probability of 7 successes if w is equal to 0.7, a w value of 0.7 is the most likely that would generate 7 successes in 10 trials, okay? So hopefully that makes sense. Now, mathematically, as we start trying to estimate more complex models and parameters, then it becomes more convenient for us to work oftentimes with the log of the likelihood function rather than the likelihood function itself. And so we can restate the preceding expression. Here, all we've done is basically log transformed each of those respective terms. And no worries, we won't do a whole lot of review of fundamental calculus here, but just to give you a sense of what's happening here empirically. So if we take that function and we differentiate that with respect to w, we have a relatively nice equation that we can solve for here. So setting that equal to 0, we find that whether we're working with the likelihood function itself or with the log of that likelihood function, either of those cases will give us the same parameter at the end of the day, 0.7, okay? And likewise, if we take the second derivative, just to verify that this is in fact a maximum, and so in this case, we can verify then that we have reached a maximum, hence the term maximum likelihood estimation, okay? And that same approach here is as demonstrated here. So when we're working with the log likelihood function, you'll notice that that log likelihood is going to be negative as indicated here. And so our best fitting model would have a likelihood function that would converge towards 0. Now, practically speaking, it's never going to get there, just like we're never typically going to observe an R squared of 1.0. But just to give you a little bit of sense of what's happening when we're trying to estimate these models, so the operations that are being conducted, okay? So the binomial is probably about the easiest way to demonstrate this. We can take the same general approach for linear regression though. And so as you may recall, this formula right here is basically just the probability density function for a normal distribution, right? So that normal distribution is characterized by its mean and variance. And so the mean in this case, we're denoting as mu, and the variance again is just sigma squared. And so if we assume any specific value for our mean and variance, we could determine how likely it is that we would observe a specific value of y given those conditions, right? If we think about how we standardize our variables, and we can determine how likely it is that our value, we would obtain a value over some range across that normal distribution. And so in the linear regression framework, we basically replace that mean value by a regression function, which in this case is just going to be x times beta, right? And so all we're doing here is modifying that function. And so this is the basis for the linear regression models that we've estimated previously. Now, under maximum likelihood, what's going to happen is we're basically going to take that probability statement, and what we're going to do is we're going to attempt to solve for values of beta that are going to maximize the likelihood here. So basically what that means is, given the sample of data that we're working with, we're going to iterate through and solve for we're going to try different values of beta, or we're going to use methods to optimize beta such that level of beta has the highest probability of generating the sample that we're observing, just as we saw in the previous case with the binomial distribution. The same is going to hold in linear regression, okay? And so we're going to take that likelihood statement, we're going to log it, because as we had indicated previously, it's easier for us to work with the log of the likelihood function. And so from there, we're just going to basically work through the algebra here. What we'll tend to find is that it's a bit easier if we work through this in matrix notation. And so the next line is basically showing you what that likelihood function would look like. And we're just replacing the square of this y minus x times a beta term. So that should look familiar to you. That's basically our residual or our error term. So we're taking that squared. So basically that quantity transposed times that same matrix. And we basically work through the solution here. I'm just taking this out into long form, and you'll start to notice some familiar terms that were introduced when we work through the ordinary least squares solution here. So we've got y prime y prime x beta, etc. And so if we differentiate that log likelihood function with respect to beta, we will arrive at a solution that looks very similar to something you've seen previously. So setting this equal to 0, we'll actually find that beta hat is equal to x prime x inverse x prime y. Does that look familiar to any of you? It should, right? Because that's the exact same solution that we arrive at when we work through the ordinary least squares. And so interestingly, we see that MLE and OLS both give us the same result there. We can also differentiate that same log likelihood function with respect to sigma squared. And working through that, setting that equal to 0, we then find at the end of the day that our variance here is just going to correspond to basically our error sum of squares here. So this is just taking each individual data point minus the best fit line, so basically the residual squared over n. So that's basically an estimate of our sample variance. Okay. Sorry, my dog's chewing on a water bottle. It's very loud. I will try to tough through it. So, okay. And so this just demonstrates that MLE is is basically straightforward for us to estimate an ordinary linear regression model. We can also use it for various other families, including logistic regression. Now, we could keep going through demonstrations, but the algebra gets a little bit more complicated as we get to more sophisticated models here. But this is just to provide you with context for essentially how we're working through and what the SPSS is using as an example when it's estimating these models, okay? And so functionally what we're doing under maximum likelihood then is we're trying to determine what values of beta, so in our beta matrix, the intercept term in each of the slopes is going to make the log of the likelihood function as large as possible. Again, keeping in mind that's going to be a negative quantity just based on definition here. And so that likelihood is basically just the probability, it's the product of the probabilities. If we take each of our individual observations, we take the likelihood function, and then we plug in the corresponding values of X. We're trying to solve for the parameters that would maximize the value of that probability, okay? And so for each observation, we calculate the likelihood for that observation, and then we multiply that product for each of the observations within our sample, okay? And then at the end of the day, rather than trying to minimize our least squares, we're trying to maximize, in this case, that likelihood function, okay? Okay, and so by analog there, the higher the value of that likelihood, the higher the probability of observing the specific sample that we're using to estimate our model, okay? And so that leads us into logistic regression. And so logistic regression is something we run into fairly frequently within transportation or within analysis and probability and statistics broadly. It's a special case for which the dependent variable is quote unquote limited. And so this would include the binary case where you've got a 0, 1 dummy variable, or cases where we have any type of discrete outcome where there might be 3 or 4 or 5 categories. Those are all different subsets of limited dependent variable models. And so if we think just about transportation, there are a number of different examples where our data would be limited. And so whether or not a driver is using a cell phone. So we'll get into this in the upcoming homework assignment. So that can obviously be classified either as yes, no, or into various categories of phone use, like talking on the phone, texting on the phone, or not using the phone. Likewise, seatbelt use can be classified as a yes, no decision. Injury severity data are generally categorical in nature. And then going back to the midterm exam, that stop-go decision is also obviously not a continuous variable. And so in these instances, since those data are not continuous, they're also going to generally not follow the normal distribution. And so consequently, in this setting, binary logistic regression, which we'll also just refer to as logistic regression or logit models is another term that's introduced, are useful for us in these circumstances. And so when we estimate these models, we typically code our dependent variable such that it's equal to 1 if the condition is true, or yes, as the case may be. And then the converse there would be equal to 0 if that condition were not true, okay? And so the thing about this is that if we try to use ordinary least squares in this setting, there are a number of problems that arise. And so we've worked through each of these previously. So looking at the assumption of linearity of y versus x, checking the residuals to ensure they're normally distributed, they have constant variance or homoscedastic, and they're independent of one another. And then multicollinearity is also the other concern there. And so if we think about these assumptions in OLS with binary logistic regression frameworks, some problems arise. And so we're going to work through in today's class some additional analyses using the data from our midterm exam. And so just to refresh everyone's memory here, we basically have data for thousands, over 5,000 drivers who are approaching signalized intersections across the US. We're observing those drivers as the light is about to change from green to yellow to red. And we're tasked with trying to estimate a model to determine how likely it is that a driver would stop in this circumstance. So y would be equal to 1 in instances where the driver stopped and 0 otherwise. And we can relate that to a number of different characteristics that would describe that specific driving scenario or that specific site. And again, you're quite familiar with that. So we work through those analyses. And as you assess the regression assumptions, and everybody in the class did notice that there were a series of violations of those assumptions. And so in this setting, if we constrain our y variable to be equal just to 0 or 1, the specific concerns that arise, our error terms tend to be heteroscedastic. Okay, now we had noticed last week those errors, they tend to be they tend to maintain constant variance until you get to either extreme of the distribution, at which case you're basically, since we're constrained at just 0 and 1, you're going to see the variance decrease as you go towards either extreme of the predicted values or of the corresponding x values, as an example. Okay. Secondly, our error terms are obviously not going to be normally distributed here because y takes only 2 specific values. And so that's why we'd see that constant rate where those residuals are either consistently increasing or consistently decreasing, depending upon whether we're looking at our predicted value or any specific x variable of interest. And then beyond that, there are a few practical concerns that arise, which we touched on a little bit, but didn't talk about in great detail. And so as one example, in the linear regression framework, it's somewhat problematic for us because we're basically modeling probabilities in this case. So how likely it is that we would see a yes or no outcome or a true or false outcome. But if we use OLS, it's possible that we can see values, predicted values of y that are greater than 1 or less than 0. And so obviously those are nonsensical. And if we're trying to use our model for predictive purposes, that runs us into a bit of trouble, okay? And so to mitigate that, what we do, instead of trying to model y directly, we are going to model the probability of y being equal to 1, okay? And so we do that by working with what's referred to as the logit. And so the logit is basically just a log transform of the odds of an event occurring, okay? And so I guess this would probably be a good point to check in with everyone. When I talk about odds, how many of you are familiar with that term? Surely someone's familiar with the term. Okay, so there's a few people here. Personally, my own background, I was most familiar with it probably from sports and talking about the odds of teams winning or losing specific events as an example. But when we talk about the odds are the ratio of the probability of an event occurring divided by the probability of it not occurring. Okay. And so back to the sports analogy, if we think about, I don't know, Michigan State football, the odds of wins in Michigan State football are relatively low these days, unfortunately. And so let's just say those were roughly 2 to 7 or 3 to 7, depending how many games. So they would have 3 wins for every 7 losses, or they'd have a 30% chance of winning to a 70% chance of losing, as an example. And we also often in the sports nomenclature, you would see the odds against an event occurring. So rather than being 3 to 7, we'd see 7 to 3 in that case. So there'd be 7 times as likely to lose a game as to win a game. Okay. And we can think about those same circumstances here in transportation. So in our case, for our midterm exam, we had the probability of a driver stopping is essentially what we're modeling with our y variable. Okay. Now we want to be able to constrain that to address some of the violations of our regression assumptions that were noted previously. And so the way we do that is we work with the odds here. So the probability of a driver stopping divided by the probability of them not stopping or going through the intersection in this case. And we're going to take the log of that. And hence the term, that's where logit comes from, is we're basically logging that odds ratio, okay? And in doing so, we're still going to have a right-hand side of that equation that's going to be linear in parameters, okay? So the model itself isn't linear, but when we log the odds ratio in this manner, we can then estimate this model such that the parameters are still linear and additive in nature in the right-hand side, okay? And so just back to the general terminology, the term inside the parentheses here, this is referred to as the odds ratio. or the odds of that event occurring. And then the logit is just the log of that odds ratio. Okay. Okay, so the big advantage of logistic distribution is that it's going to constrain our probabilities such that they lie exclusively in that 0-1 interval. And so we don't have predicted values beyond 1. We don't have negative predictions for probability. And so under this framework, we can determine the probability of y being equal to 1 using the general equation we see right here, okay? So we take that linear function on the right-hand side on the preceding slide. So the exponential of beta x divided by 1 plus the exponential of beta x gives us that probability back, okay? And so just to refresh where that's coming from exactly. So we're exponentiating both sides of that equation. And so our probability, for example, of a driver stopping would just be the exponential of that function divided by 1 plus the exponential of that function. Stated alternately, it would be equivalent to 1 over 1 plus the exponential of negative beta x. And that's just going back to the underlying calculus here, okay? And so that's the framework that we're working in. And so if we compare just a linear probability model like we had estimated last time with the logistic regression model, for our driver decision model, we had this circumstance where we had a lot of observations where the predicted value ended up being less than 0, and a number of cases where the predicted value was greater than 1, when in actuality we had a bunch of points that were just clustered along these lines, right? Because we're only observing 0s and 1s. And so the logistic regression model basically circumvents that because it takes this general S shape. And so that S curve is going to asymptotically approach 0 on this extreme and 1 on this extreme, for example. Or alternately, in some circumstances, we may see the S curve in the opposite direction. So it may be very likely at small values of x and very unlikely at large values of x, but we would see that same general S curve as opposed to the linear model. And so obviously, if we think about the points being clustered along these respective models, the red line or the red graph is going to fit those data much better than the green in this instance, okay? And so when we're trying to interpret what the coefficients mean in this case, in linear regression, it's straightforward, right? Beta indicates the change in y that would be associated with a 1-unit change in x. Now, in this case, it's somewhat similar. So our beta is telling us the increase in the log of the odds that would occur for a 1-unit change in x. Now, the problem there is simply that there's not a straightforward interpretation of that. So if I told you that the log of the odds increased by 0.2, you would say, what does that mean in essence, right? And so rather than talking about the impacts of beta on the log odds, it's more intuitive for us to talk about how that variable would change the odds of that event occurring, okay? So if we say the odds double, that makes a lot more sense to us than saying that the log of the odds double. And so to that end, if we want to express these outcomes as a function of the impact on the odds, we're just going to exponentiate both sides of this equation. And so in doing that, when we're estimating these regression models, we can take the model parameter and just exponentiate it. And that's going to give us a practical sense of what the impacts of that variable are on that outcome actually occurring, okay? So the exponential of beta for any specific variable, we'll just denote it as x sub j in this case. As x sub j increases by 1 unit, we're going to see an e to the beta j increase in the odds of that event occurring, okay? Now, beyond that, one other difference that occurs when we're working with logistic regression models, we don't have the same type of metric when we think about R squared as an example. And similarly, when we're working with maximum likelihood, we don't have the familiar F-test and items of that nature. And so as standard output, there are a number of different metrics that can be utilized. We'll talk very briefly about 3 of those here. Okay. So rather than the F-test that we would use from an analysis of variance in linear regression, where that F is just basically simultaneously testing whether that collection of parameters
provides an improved fit, or whether any of those effects are significantly different from zero. What we're doing in this case, as we add variables to our model, we're basically examining how much improvement we see in the goodness of fit. And so the way we're doing that, our restricted model is basically a model that's simpler in form. So it's not including those other variables of interest. As we add variables to the model, we remove those restrictions. And so the unrestricted model is the more flexible model. And so keep in mind, these log likelihood values are going to be negative. And as we add variables to the model, that log likelihood is going to improve or increase. It's going to approach towards zero, which means this quantity is going to be, both these quantities are negative, but this quantity is more negative. So as we add variables, the unrestricted log likelihood is going to improve our goodness of fit. And so this entire quantity then is negative. So that's why we're multiplying that by -2 here, because that gives us a positive number. And that test statistic, we refer to that as our likelihood ratio test statistic. That's going to basically follow a chi-squared distribution. And the degrees of freedom are simply going to be the difference in the number of parameters between those models. Okay, so as an example, if we add one predictor variable to our model, we'd evaluate the improvement in goodness of fit, and we compare that against the chi-squared statistic with 1 degree of freedom. Okay. Alternately, if we were comparing two competing models, one of which had, say, 3 parameters and one of which had 6 parameters, we take the difference in the log likelihoods, basically double that difference, and then we compare that to a chi-squared statistic with 3 degrees of freedom. Okay, hopefully that makes sense. And so we can evaluate that chi-squared statistic to just determine whether or not that model is essentially useful, or whether any of those parameters have a meaningful impact on our probability or our log of the odds, or the odds of that success occurring. Okay. All right. Secondly, there's not the same type of metric in terms of R squared here, so we can't partition the variance as we do in the linear regression case. What we can do is basically look at the goodness of fit we see between those unrestricted and restricted models. So again, keep in mind here that unrestricted model is the model that has more parameters. And so in the best case, what's going to happen is that term is going to converge towards zero, basically, right? And so when we look at this ratio here, as that goodness of fit improves significantly, this value is going to get closer to 1. Now, in practice, what's going to happen, it's never going to actually get to 1, just like we see in linear regression, unless we've got something wrong with our model. But this is one of several metrics we can use to provide just a qualitative comparison of different competing models on the same data set. Okay. And then the last item that's good for us to look at as a potential diagnostic for how quote unquote good our model is how many observations are being correctly predicted. Okay. So at the outcome of this, once we've estimated our model, we can use that model and plug in the values for any specific observation, and we can determine the probability of a yes, or of the probability of y being equal to 1. Okay. And so that probability is going to range between 0 and 1. And so what we'll typically do, if that probability is greater than 0.5, we'll assume it's predicting a yes, or it's predicting that y would be equal to 1 for that specific observation. If it's less than 0.5, our model is basically predicting that it's more likely that y would be equal to 0 in that case. And we can basically look at a cross classification table that shows us how many instances we're correctly predicting a yes, correctly predicting a no, and then incorrectly predicting either of those outcomes as well. Okay, so if we think about a decision matrix, for example. Okay, so we'll demonstrate this in a few minutes using SPSS, but I think that was, yeah, so that was a quick introduction before we go into SPSS for the remainder of today's lecture. We'll come back next week and we'll expand this, and we can take the same process we're talking about today for variables with 2 outcomes and apply it to circumstances where a dependent variable takes 3 or more values potentially. And like I said, assignment 4 is now out on D2L. That will be due a week from Sunday. And preliminary results for the term paper, I'll plan to check in with each of you individually via email in the very near future. But our plan is to have some preliminary results by April 11th. Some more details to come on that. And then we'll have a few additional weeks after those preliminary results for us to finalize our analysis for the term paper. Okay. Now, just very quickly, assignment 4, just to give everybody context here, this is basically data that were drawn from a driving simulator study that was conducted where we had drivers from 3 different age groups. And so in this circumstance, the simulator was set up basically such that the signal would go from green to yellow to red at certain intervals relative to where the driver was located. And so typically the light would change when that driver was either 3 seconds or 3.75 seconds away from the intersection based upon their travel speed and the distance to the intersection. And so the reason those values were selected is that most individuals would tend to go if 3 seconds were available, and they would tend to stop if 3.75 seconds were available. Now there's a lot of noise and a lot of variability there, but we can control for some of that. And so what we're looking to do using these data is to basically determine how likely it is the driver would stop or go through the intersection, while also taking into consideration whether or not they were distracted. And so in this case, there were various types of handheld and hands-free cell phone use scenarios. And so this will allow us to compare differences across those various settings. Okay. So to get everybody ready for that, we're going to transition to SPSS real quick. As I'm doing that, does anybody have questions on anything we've done up to this point? Okay, if not, I'm going to take us into remote desktop. And so you can feel free to work along in parallel on your end, but this data set should look very familiar to everyone. And so what we're going to do real quick, so traditionally we've gone through and we've done linear regression models from the dialogue here. And so as an example, if we estimate a model for that stop-go decision as a function of distance, we will get the output, the standard output that you're all familiar with and see right here. And so our model results, that constant term minus 0.087 and the parameter estimate for distance is 0.003. We can get those same results. So this is all done by ordinary least squares, okay, under the standard platform here. We can also go through and we can go under this generalized linear model framework. And so this allows us to estimate linear regression models and a bunch of other different families of models. The big difference here is that this platform uses maximum likelihood as opposed to ordinary least squares. And so I'm just going to replicate that exact same model we saw previously. And so it's a bit more complex in terms of actually using this generalized linear model. So we're going to first of all need to select the type of model. And so we're assuming linear, and we'll get to logistic regression in a second. I just want to demonstrate maximum likelihood real quick. Our response variable, again, is stop. Our predictor variable, we'll use distance in this case. Now, instead of just hitting OK there, and let me just demonstrate. If you try to hit OK after entering our covariates, you're going to get an error message that tells you we're estimating an intercept-only model. And we can do that. But after you've added your predictor variables, you actually need to go over to model and move those over to the model box here. Okay. And the reason for that is there's a bunch of complexity that can be introduced here in terms of interaction effects between those variables. But generally, we're just interested in the main effect. But this is just to inform you, you need to fill out each of these 4 tabs in order to estimate the model that you're intending to estimate. And so as we look at the output here, you'll notice we obtain the log likelihood value. And so negative 2834, as we add variables to the model, that's going to increase and get closer towards 0. we see our chi-squared likelihood ratio test here. So that number is very large. And so that's going to be highly significant. So p-value less than 0.001 in that instance. And then we get down to the very bottom here, and you'll notice that our parameter estimates here are the same as we have seen when we estimated this using ordinary least squares. Okay, so an intercept of negative 0.087, parameter estimate for distance of 0.003. Okay. All right, and so at this point, I'll show you, we can estimate logistic regression models either directly from the regression menu here. So you'll notice binary logistic. This isn't quite as flexible as the generalized linear models I showed just a moment ago, but what we'll do here, we'll estimate that same simple model, so that stop-go decision as a function of distance, and then we're going to hit OK. And so as we look at the output here, the first information that's provided is just a summary of our data. And I haven't talked about this previously, but if we have missing cases, those are basically thrown out of our analysis data set. In this case, that's not a concern. At the starting point, so what it basically does, it's building this model in steps, adding variables to the model. And so it starts with just a simple model that includes only a constant term. Okay. And so if there's only a constant term in that model, every observation is going to be predicted to either stop or go, as the case may be. Now, in this case, 52.8% of the drivers had actually stopped. And so our model is going to predict that all the drivers will stop, when in actuality, only 52.8% of them do. And so from a discriminative standpoint, this isn't doing a very good job of helping us to classify which cases were stop versus go. Okay. Now, as we add variables to the model, we'll notice that we're going to see significant improvements in goodness of fit. And as we look at the output here, this classification table tells us for the model that includes just distance as a predictor, we're correctly predicting roughly 74% of our observations. Okay, so reasonably good performance. We like to see very big numbers in the diagonal. So these are correct zeros, correct ones, and then incorrect predictions here. Okay. And so lastly, if we go down to the very bottom here, this is where our model output appears. And so we've got our constant term and we have our distance variable as well. Okay. And so just looking at those variables really quickly, what we can do is we can actually calculate the corresponding probability of any specific observation of that driver stopping just by plugging in whatever their distance was from the intersection at the time that signal transitioned from green to yellow, essentially. Okay. And so as you can see here, as that distance increases, we can exponentiate this, as you see over here. And so what that's telling us basically is for every 1 foot increase in distance, we're seeing a 0.15% increase in the odds of that outcome occurring. Okay. And in instances, now you'll notice it's also providing us with an odds ratio for the constant term. I don't know why it does that, because that doesn't really make any sense to us. It's just standard output here. But what we can do, if you have a variable with a positive coefficient, so if beta is greater than 0, the odds ratio here is going to be greater than 1. If you have a negative coefficient here, this is going to be less than 1. Okay, just given the nature that we're exponentiating those values. So 0 is basically a threshold. If beta was equal to 0, if that variable had no effect whatsoever, then this would just be equal to 1. So it wouldn't have any impact on the corresponding odds ratio. Okay, does that make sense? All right. And we've also got some estimates of different R-squared metrics that are provided for us right here, which again, this isn't the same R-squared as we would see in linear regression. So the magnitude of these values tend to be significantly smaller. So in a lot of cases, an R-squared of 0.1 or 0.2, or in this case, 0.3 is actually quite good, just given the amount of variability that's inherent in the data here. But as in the linear regression case, this is really only useful for comparing competing models on the same data set. So if you had two completely different models with different R squared metrics, that you couldn't necessarily say that one model is better than the other, because that's partially a function of just how much variability there is in that process we're observing. Okay. And so we can continue to, we can continue to build out these models using that binary logistic regression framework. So in addition to distance, we can include speed, presence of auto enforcement cameras, various other variables. And as we add those to the model, as you can see down here, this is basically demonstrating to us the relative impacts of each of those variables. And so in the case of speed, the converse is true to what we've seen previously. So as the speeds increase, the drivers are going to have less time to react, and so they'd be less likely to stop. And so you'll notice in that case, if we increase the speed by 1 unit, which in this case would be 1 mile per hour, we'd see roughly a 15.3% decrease in the odds of that person stopping. Okay. The other variables, again, are positive, and so those odds ratios are greater than 1 in those cases. And so as an example, if auto enforcement is present, the parameter estimate is 0.235. And so if we exponentiate that, we see that the odds are 26.5% greater that a driver will stop at a location that has auto enforcement versus a similar location that does not. Okay. And so as you can see here, it's relatively similar to what we've done in linear regression in terms of the interpretation. It's just slightly different given the structure of the model here. Okay. I also wanted to quickly demonstrate we can estimate the same model under that generalized linear model framework. So instead of a linear regression model, we can estimate a binary logistic model. Everything else will essentially be the same here. I do want to demonstrate one important point here, though. So I'm going to scroll up to the preceding results real quick. Just note the constant term was 0.657 here, and then we had 2 positive and 1 negative coefficient. If we scroll down, oh, I didn't estimate the same model. Brilliant. Let me add those other predictors in real quick, and then I will compare the results. And again, just a reminder, you need to pull all those over at the same time. And now what we'll notice here is that the signs have all flipped, okay? So instead of our intercept being positive 0.657, it's now negative 0.657, and each of the other variables have flipped here as well, okay? Now, you might wonder why that's the case, and for whatever reason, when you use the generalized linear model framework, by default, what it's going to do, you've got to see this little footnote up here. This procedure models 0 as the response, treating 1 as the reference category. So I'm not entirely sure why they've structured this model to work in that manner. But what that basically means is that all of these parameters are backwards from what they should be. So we can actually correct that. So I'll demonstrate that right now. So as we go here under response, you'll notice where it says reference category here. Now, by default, it will use the highest number as the reference category. So in this case, it will assume 1 is our reference case. We would prefer to set it up logically. So 0 would be our reference case. And so we're going to change our reference category to the first or lowest value. And then we'll rerun that analysis, and now we'll see the correct results at the end of the day. Okay, so it's again positive 0.657, and all the other parameters are consistent, at least in terms of what the direction of those effects should be. Okay. The other reason I wanted to quickly demonstrate this to you all using the generalized linear framework is because this also allows us to estimate a model that includes only a constant term. And so I just quickly wanted to demonstrate for everybody. I'm going to estimate a linear regression model here. Okay. So back to the linear framework, just for demonstration purposes. Our dependent variable is stop. I haven't included any predictors in my model, so I'm going to hit OK. It'll give me a warning that it's going to estimate an intercept only model. I say, yes, that's fine. And so we go down and we see our intercept term here is equal to 0.528. And can anybody remind me what that 0.528 means? So real simple linear regression model. We only have a constant term. So that 0.528 means what? It looks like we've got an answer in the chat box. Y bar, yeah, exactly. So Y bar in this case would be essentially the probability of stopping across that entire sample of drivers. So 52.8% of those drivers have stopped. Okay. Now I bring that up because I'm going to go in and I'm going to also estimate a constant only model, but this time I'm going to do it in the binary logistic framework. Okay. So logistic regression, stop is our dependent variable. I again have no predictors. And yes, I want to estimate a constant only model. And so as we scroll down to the bottom here, instead of 0.528, I see 0.112. Okay. And so now what I want to do, I don't want to have to switch what platform I'm sharing with you all. So I'm just going to do this manually here. But I just want to, I'm going to demonstrate, I'm just going to create a variable called pstop. And so what I'm doing here, if we take the exponential of 0.112 divided by 1 plus the exponential of 0.112. Oh, what am I missing? Does anybody see my missing operator there? Okay. And so I'm going to look at that real quick. So I could have done that quickly on a calculator, but so what you'll see right here, 0.53, so that's basically the 0.528 number, okay? So if we're estimating a constant only model, we get the exact same result in either of those cases, okay? Now, as we start to add variables to the model, we're gonna see substantial divergence, obviously. And just to kind of demonstrate that, we'll go back and return to that same linear model we'd worked with previously. So let's just include speed and distance and auto enforcement as the covariates. And so in the linear regression framework, these are basically telling us what the average effects of those different variables are on our baseline probability. Okay, so there's it's 3.8% higher probability of stopping where auto enforcement is present. There's a 0.3% increase in the probability of stopping for every 1 foot increase in distance, and so forth and so on. You'll notice the constant term here is now 0.554 after accounting for those other factors. And then when we go in and we instead run this as a binary logistic model, we obtain these estimates. And so in this case, we're finding that the sign and the general direction of these effects are going to be quite similar. But if we try to equate the actual magnitude of those differences, so the changes in probability of stopping between when these variables increase by 1 unit, we are going to see some substantive differences there. That's going to be particularly true if we have probabilities that are relatively low or relatively high, as an example. So if we look at things like seatbelt use rate, the vast majority of people wear their seatbelt, or the probability of someone drinking and driving, that probability tends to be quite low. And so in those circumstances, we'd see dramatic departures between the linear regression and the logistic regression settings, okay? In cases where the probabilities are close to 0.5, as it is in this case, we'll tend to see general agreement until you get to extreme values of any of these variables. So at very long distances or at very high speeds or very low speeds or low distances, as the case may be, we'll tend to see the most marked differences between the linear and logistic regression frameworks. Okay. All right. So that's a very quick overview to logistic regression. Do we have any questions from the audience here? You're free to kind of play around with things here. Like I said, the homework assignment for this week kind of builds naturally off this because we're analyzing basically the same dependent variable of interest, just with a slightly different data set and a slightly different context, but you should all be in fairly good shape there. So questions from anybody?
Um, can you explain a little more about interpreting the data for the logistic regression?
Sorry, say that again, Falarin.
What can you explain a bit more about interpreting the coefficients for the logistic regression?
Sure. Now what I'm going to try to do here, I know I demonstrated last time how bad I am at using the whiteboard, but can you folks all see the whiteboard?
Yeah.
Okay. So, oh, it's green. Okay. So if we look at the log of the odds, so this is the general setup of our model here. Uh-oh, come back. So we have this general structure, right? E1 plus beta 1, x1 plus, and then dot, dot, dot. Okay. And this becomes increasingly less fun the more you have to use this, at least with a trackpad. So if we look at the model that we had just estimated, we basically had in that case, okay, this is a little easier. Well, I guess let's be as equals 0.657 minus 0.166 times speed plus 0.026 times distance plus 0.235 times auto enforcement. Okay, and so as we look at this quantity, like I said previously, the effects of any of these individual variables, if we exponentiate any of these coefficients, so if we exponentiate 0.026 and that's going to give us 1.026. So for that specific variable, the odds ratio here, so P over 1 minus P is going to increase by 1.026 when distance increases by 1 foot, right? in addition to that, one item that's also, so the odds ratios are telling us what the change in this quantity are. Okay, the odds, so probability over 1 minus the probability. If we wanted to compare this directly to what we saw in the linear regression framework, so and this probably makes sense, and this is the way I prefer to look at it. I would be interested in what the change in P is, that probability rather than the odds. Okay. Now, it's a little bit more involved to get to that calculation, because what you would need to do essentially is you would take the model results, and we could assume the mean values for every other variable in our model. And then we could basically change our variable of interest from 0 to 1. Okay. Now, it's a lot easier if I actually demonstrate what I'm talking about here. So let's say, for example, if we wanted to look at the change in P. So in that case, we can plug in mean values for all other x's and then increase our variable of interest by 1 unit. Okay. And so bear with me because it's going to take me a minute to do this. So, sorry, I'm trying to toggle between remote desktop and, well, let's to try to make this as seamless as possible here. If we just assume specific values here, so just to clarify, these are assumed values. So if we assume mean values of, let's say 30 miles per hour for speed, 100 feet for distance, and 0.5 for auto enforcement. So none of these are actually the real values here, but this is just for demonstration purposes. And so if that was the case, we could then determine that the probability of stopping is equal to 0.657 minus 0.166 times 30 plus 0.026 times 100 plus 0.235 times 0.5. And so, I'm sorry, that's not, that's an intermediate step to get to the probability of stopping. So let me just clarify that real quick. So I'm quickly going to calculate that. That gives us minus 1.6055. Okay. So that is that term there. That's basically our beta x. And so our probability of stopping is going to be negative 1.6055 divided by 1 plus negative 1 point, or sorry, I almost forgot to exponentiate. We're going to exponentiate negative 1.6055 divided by 1 plus the exponential of negative 1.6055. And so under these conditions, so if we've got a 30 mile per hour speed when the light turns, if that driver's 100 feet away, and if there's auto enforcement present, then their probability of stopping is going to be equal to 0.17 roughly. Okay, so they'd have a 17% chance of stopping in that case. Okay. Now, if we wanted to determine the probability of stopping under those same conditions, but as we get to, let's say, 200 feet upstream, so distance equals 200, we would go through and calculate that same quantity, 657 minus 0.166 times 30, 0.026 times 200 plus 0.235 times 0.5. And when I do that, we get 0.9945. Again, sorry, the intermediate steps there, Bx equals. So that's 0.9945. And then our probability of stopping back to the initial point here would be the exponential of 0.9945 divided by 1 plus the exponential 0.9945. And in our case, that would be equal to 0.73. And so that demonstrates there's a very pronounced impact as we increase that distance by 100 feet, right? Our probability of stopping goes from 0.17 to 0.73. Now, we typically work with odds ratios. So Falarin, sorry, this was a very rambling response to your question. But we work with odds ratios in part because they're relatively straightforward to interpret. And then secondly, they're very easy to calculate. All we need to do is exponentiate, okay? Now, instead of the odds ratios, we're often interested in what are referred to as marginal effects. And so that's basically, if we increase a variable by 1 unit, what happens to this probability instead of what happens to the odds of that event occurring? And so when we do that, it's just a bit more involved because what we would need to do, we don't have, since this is a nonlinear function, it's really important what values the other variables take as well. And so there are two general approaches to working through this in the literature. The first of those is you can plug in the mean value for each of the other predictors, and then you can just increase whatever your variable of interest is by 1 unit. And so I could increase that 100 to 101. I did 200 in this case just because that shows us a more pronounced difference. But we could do that, and that would give us an estimate of what that average effect is. A second way we could calculate that is we could take every individual observation in our data set and all of the actual X values, and then we could increase X by 1 unit for all of those and average that across the sample. Either of those approaches is going to give us a result that's very similar in nature. But that would tell us then what the impact of increasing that variable is on the probability rather than the odds. Okay. So it's presenting us the same information, but in a slightly different context. I have no idea if that even answered what the intent of your question was, though, Falarin. So was that helpful, or did you have further questions?
It was helpful. Thank you.
Okay.